Recording in progress.
Okay, so one thing you could do for this problem, if you do, I mean, the first thing you should always do is always just plug in the number, see what happens, right? Just plug in the number, see what happens. And because these problems are written for a purpose, because I want things to be weird, I want you to start using other techniques. When you get 0 over 0, that's indeterminate. Remember, 0 over 0 could be any number. We don't know. 5 over 0 is undefined because that just, that's the number that can't happen. But 0 over 0 could be blanking. So that happens. It means there's going to be probably a limit, but we'll have to do some other techniques. You could plug in a number close to 4. It take a little while. You might need to calculate like 3.999, 4.001. You graph it, right? See when I get close to 4, what happens. And if you do any of those two things, I believe the answer is going to be 1/5 or 0.2. Now, how did I know that? How did I do that in my head so easily? I didn't calculate 3.99, 4.01, or I didn't graph in my head. What I did was I factored. I factor the bottom. And what I simplify? So I get 1 over x plus 1. And then if I plug in 4, I get 1/5. That is what we're going to have to be doing often today. It's algebraic techniques. That is actually the preferred way to do it because it gives you a little more confidence in your answer, and it's more accurate anyway. Now, the one thing I caution you about, if you write your answer like this, you're going to lose a place. Why are you going to lose a place? You got to write the limitation. Got to write the limitation, 100%. On the AP exam, you would actually not get points. They would actually nail you for this on the free response. So you have to, it's a pain in the ass, I know, but technically speaking, we're still dealing with the limit, right? We haven't plugged in 4 yet. Until you finally do, you got to keep writing it until every time. Yeah, I know it's a pain in the ass, but you got to do it. So now I know, and then once you plug it in, you're good, 1/5. Yeah, it does. Okay. Now for part B, I'm sure you guys got it, but let me show you the technique that you can use algebraically. Yeah, go Oliver.
When you're like writing your final answer, can you say limit x approaches 4 f of x, or do you have to write the actual function?
The actual function. Yeah. Oh, well, I mean, well, if it's simplified, yeah, because what you got to write simplified. I mean, are you talking about?
Like, I was asking if you could write just like f of x.
Oh, sure, that's fine. Yeah, that's fine. Sure. I didn't know you were asking, but now I don't. Okay. I would find the LCD for the numerator. Right? So you have 4 minus x plus 1 over 4 parentheses x plus 1 all over x minus 3 over 1. You got to flip. We'll clean up stuff too, obviously. So it's what? Negative x plus 3, 4x plus 1 times 1 over x minus 3. And again, I'm leaving space so I can actually write the limit notation. Yeah, the negative x plus 3 is the same as saying negative parentheses x minus 3. It's a little sneaky there. So now it's negative 1. And now let's plug in the 3, which would be negative 1 over 16. Or it's like negative 0.0 something. So I can't remember exactly the decimal. So negative 0.0625, I think. Yeah. Yeah, okay. Now, these here are some special cases. This one is going to be just 1. And that one's also going to be 1. If I'm correct on that one. And graphically speaking, it looks like this. Oops. I think. I can't remember, actually. We'll cross that bridge later. But I know it's 1, and that's 1. This right here, x squared minus 1, x squared plus 1. Quiet, guys. Thank you. And then that's the difference of cubes. Well, we will get difference of cubes in a sec. X minus 1 And don't forget your limit notation. X squared minus 1. Or x cubed minus 1, sorry. I just can't do threes. I need a stylus. Is that what you're asking, Catherine? X cubed plus 1?
The other one, the last one.
Oh, the answer for this one? Negative 1 over 16? 1?
Like x plus 1, like what's after that?
X squared plus 1. X squared plus 1? Or x cubed plus 1?
But how does x negative 1, x plus 1 turn into?
Okay, so that's if it's a square, right? X squared minus 1, x squared plus 1.
But that's what the denominator is. Like,
The denominator, yeah, so that's x cubed minus 1, x cubed plus 1. Oh! Sorry, I made a mistake. Catherine, you're just so awesome with correcting the teacher. Just like the honors cards. I forgot to do this. My bad. It's x squared minus x plus 1, right? My apologies. Yeah, because that's the difference of cubed. I messed up. That's my fault. Yeah, I messed up. Okay. And actually, that's supposed to be x minus 1. Gosh darn it. Here we go. Thanks for correcting me. Okay, so now things will cross off. These will cross off, right? And now when I plug 1 in, I get 2 times 2 over 1 times 2. So get 2 altogether. So that's the answer for F. Yeah, Audie, go ahead. Did I make a mistake?
Isn't it x plus 1 times x squared minus?
Oh, you're right. I made another mistake. Yikes. Thank you. Yes, thank you, Audie. So that should be 2/3. My bad. You get 2/3?
Yeah.
Yeah, much better. Okay. For D and E, actually I might need my calculator for that one. Or I'll go to Desmos because I don't know those off the top of my head. And what was it? Natural log of x plus 1. Yeah, 0.693. Now, I overheard someone say L'Hopital's rule. Okay, that we haven't taught to you guys yet. That's interesting that you said that. It's a rule. Audie said that. So right now we'll say 0.689.
So I just.
You looked it up?
No,
You know, how do you know it? It's a derivative.
I'm.
Oh, okay. So that's all good. Yeah, good, perfect. Well, I'm not ready to teach that yet. I'm not ready to teach that, but it's well, for now we'll say 0.689. There is a calculus technique we'll do down the road. And then for the last, actually, sorry, that was this one. My bad. Yeah, for now, just give it that. Just graph it for now.
Yeah.
What was that? No, I did ln. Sorry, I did no ln. That's what I meant to say. Oh, it's approaching 0. Oh, I did 1. I don't know why I did that. That's dumb. Okay, no, I trust you guys. Let me go back. Hold on. Yeah, that's correct. Yeah, it gets close to 1. You're right. Then y equals parentheses e to the x minus 1 divided by x. Yeah, it's also 1 as well. Yeah. So okay, there we go. We're all set. Okay, we're good? Yeah. Okay. So let me go and clear that. Actually, and this was what was this one again? That was 1/5. Yeah, let me just save this as a screenshot. Here we go. Okay, for 2, what you can do for this one is kind of just look at the graph. If you're going -2 from the right side, we'll say it does not exist. Or you can say negative infinity. I'll accept that as well. Captain, go ahead. Oh, from the right. My bad. Wait, no, pause infinity. Yeah, my bad. What was your question, Catherine? Okay. -2, now that does not exist because the left side does not equal the right side. 0, that does not exist because it's 2-side limit and left side does not equal the right side. 2 in general is going to be 1/2, we'll say. 4, we'll say it does not exist. Or you say pause infinity. And that 4 will say is 2. The limit does not exist though for 0, right? Yeah. Yeah, and then we haven't really talked about the types, but I'll kind of tell you the types right now. This is called infinite discontinuity. This is because the LHL does not equal to RHL. Left-hand limit, right-hand limit. This right here we call a jump discontinuity. Here, that's also infinite discontinuity. And technically speaking, at -2, that's also infinite discontinuity as well. But more specifically, left-hand limit does not equal the right-hand limit. So those are the reasons for that. Okay, let me save that. I'll make sure this goes to school G. Okay, for 3. That one won't exist. That's because the graph looks like this, right? This one, graphically speaking, if you shift 2 right, that also does not exist. And this one, I think it's oscillating. Because 1 over x. Cosine would be the same thing. Yeah, let's do it really quickly, guys. Yeah, it oscillates. Yeah, because cosine could be, it's a 2 pi cycle, right? I mean, there's so many different things that could happen. Like if you plug in 0.1, you get cosine of 10. But if you plug in 0.01, they have cosine of 100. It's going haywire at that point. So yeah. It's not, we don't know. We just don't know. And then by direct substitution, that's 1. That's sine pi, which is 0. And that's cube root of 1. All right, let me save that also. C is 1? Oh, 0. You're right. Okay, I'll need to delete that. Okay. Yeah, good. And we didn't do 5, so we won't do 5. I just plug in 1, sine pi. Yeah. You said what, sorry? Oh, it might be just a typo. Yeah, or it might be a formatting issue. Okay, I think that covers the homework. So let's now move on to notes, guys. And let me just update. One sec. Okay, guys, we're gonna finish off the notes. So let's go to page 6 because we did substitution last time, right? So sometimes you can just substitute, and that's fine. Now, This is where things get a little funny. Guys, quiet, please. Thank you. Root x looks like this. We should know this, right? Always spent all these years graphing and understanding, because that now we just cannot. That can't be an issue. We got to make sure we're comfortable with graphing these, understand how the graphs look, right? So that's root 4, which is just 2. Very easy, right? Now here's the problem with this one. Actually, this is wrong. So don't do this. Someone will say this, but why is that wrong? Yes, thank you, Duke. Wow, good. Excellent. Yeah, so this one's actually going to be D&E. And that's because there's no left-hand limit. And why is there no left-hand limit? That's because root x is not defined for x less than 0, because it's imaginary otherwise, right? Now, what you could say, or what you should say, is this. The limit as x approaches 0 from the right side of root x, now that's 0. That you could say. Let me make that 0 a little better. Sorry about that. And that's what we call an RHL, a right-hand limit. Okay? Right-hand limit. Okay, we're cool? All right. Yeah, I know. It's terribly exciting stuff. Sorry. Okay. No limits, right? No, trust me, it does get really exciting down the road. Let's get some really juicy problems here. All right. Here, yeah, if you do direct substitution and run into a problem, you have 4 minus 4 or 2 minus 2, which is 0 over 0, and that's a problem, right? That's indeterminate. We already talked about what that means, right? So what you want to do is simplify, right? But you got to write the limit notation first. I think I'm gonna have to buy a new stylus because this is too hard for me to do on the mouse. Gone. Plug in 2, you get 4. Right? That's all. Okay. Now they get a little more exciting. Strategy 3. If you see a radical, consider the conjugate. You guys know what conjugate means? What does it mean? The opposite. Change the sign in the middle. Yes, good. Because I don't have much room here, I'm going to rewrite it. I'm going to rewrite the problem first. Are you guys getting sick? There's allergies. Okay. No, let's go and make sure I don't want to get sick. So you got to do this. Okay. So you have x plus 1.
You do it too. It's fun. It's fun.
Okay. So guys, quiet, please. Thank you. So let's clean it up. Obviously, the top becomes x, right? And the bottom still has another x. What happens to those 2 x's now? They cancel out. So it comes out very nice and clean, right? That's what we want. These problems are written for a purpose, that things will come out nice and clean. Now you can plug in the 0 afterwards. Yes, I do need to keep writing my limit notation. I'm just being a little lazy right now. Once you plug in, you do not. No. Once it's plugged in, you go straight. I know the answer is 1/2 now, and I'm done. So, but yeah, that's for sure. And here's the thing. I'm still grading your other tests. I'm also grading. Actually, I'll hand it back today because I do want to give you guys a little time to get some head start to homework. They're going okay. So we're fine. But this stuff, just so you know, I'm done doing. Like that was a tough test. I'm making this incredibly straightforward, just so you know. Like this stuff is going to. Well, there might be one. Might be one problem I throw, but maybe one small one, small. But for the most part, yeah, because calculus is very foundational, I have to keep this very concrete for you guys. So like, there's a problem you can see, right? And you know what to do now, right? So it's a conjugate. Other one might involve complex fractions, which I kind of showed you guys already. But let me do it again. And remember, you gotta find the LCD.
Oh, wait, you don't have that. Instead of that. Why is this multiplied by?
Yeah, what's up? Because I'm a space cadet right now. That's why. Because Friday. That's why. Thank you for correcting me. Thank you. Okay, correct me if I'm wrong, guys. I make a lot of mistakes. But I'm gonna talk myself. Yeah. So, good. Yeah, so clean it up, right? Let's clean up. So you should have, and I think you guys kind of know what's gonna happen. So I'm just gonna kind of skip some steps here. The bottom will flip. The top will have 3 parentheses x plus 3. And the top should have negative x. I think hope you guys can see that. And it's -1 because x's will cancel. -1/9, you got it. Yeah, if you plug in a calculator or graph, you get -0.111 repeating. So yeah. Okay. Lastly, for piecewise functions, you gotta be really adept with piecewise functions, so you know. One thing when I taught AP Calculus AB in the summertime, there's usually a review packet, so you guys will get that whether you do AB or BC. The AB packet, we heavily emphasize the piecewise functions. Probably do the same for the BC packet. I've never seen the BC summer assignment. I don't know what that looks like, but we don't want this to be an issue because we do lots of piecewise functions in AP Calculus. So, so you should be pretty comfortable. If you're having some trouble, I could give you guys some worksheets on it. But you want to be pretty comfortable with graphing piecewise functions. And what I usually do is I'll start the boundary, which is 1. Plug 1 in, which I know is going to be 0. Then just follow the slope, right? You're of course going less than 1. Some people like to graph the whole thing and erase what's kept. That works too. But kind of the quick and the easy way is like, hey, plug in 1, you get 0. Let me make a few tick marks actually. Okay, so 1 is 0. And it's a whole, by the way. Are you good?
I have a question about notation. If I say the limit does not exist, do I say limit equals DNE?
No, just say D&E. It's just a word, it's a phrase, does not exist.
Okay.
Or you can write the limit does not exist. It's not an equal thing, it's just more a condensed phrase, that's all it is. Yeah. But yeah, great question. And then let me switch colors for a bit of contrast. Plug in 1, I get 1, right? I think so, and it's included. And it's parabolic, where the vertex is at 1, I think, right? No, it's at 2. No, the x-intercept at 2. So there's an x-intercept at 2. So yeah, the vertex is at 1. And does that. Okay. So now part A. So 3, which one I'm going to go with? The second one, right? So at this point, you could just actually just plug it in. So I'm just plugging it straight up. I get -3, right? For part B, it's D&E. And that's because the limit as x approaches 1 from the left side of f of x equals 0. The limit as x approaches 1 from the right side of f of x is 1 because the LHL is not equal to RHL. The limit does not exist. Yeah. Or you can say limit of whatever does not exist. Yeah.
Do you have to write out all those stuff where it's in question?
If I asked you to verify, yeah. Yeah, actually, what Kate asked was fantastic.
It's early, because, you know, AP, I mean, you guys have APs for other stuff next month, right, or a few weeks. This AP, you're not gonna do until May of 2025, right? They are huge, let's say they have call for is huge on justification, huge. So you do have to justify and show reasons, state reasons, so I'll make it, you guys a habit of that.
I'm basically teaching guys like AP students right now. This is like, actually, this is AP Calculus AB. Think of it this way. You guys are in the first few weeks of AP Calculus AB. I'm going to force you guys to start doing the justifications. You have to get in a habit of that next year as well. So, yeah, I'm not. That's one thing I will be tough on for sure. I'm usually pretty lax most things. I'm pretty tough on this stuff because you have to get in that habit of justifying. So you have to state reasons, and we'll talk about that. Okay. All right. So that covers those notes. Now the next set of notes. Let's see how far we can get. I want to get to page 4 if we can. That'd be lovely if we could. I think we can. I don't want to do continuity because continuity is something to save for Monday. I really want to do more stuff on limits and just kind of tell you what's happening here. So let's go back to Desmos again. So now we're on part 2 of the notes, guys. So if I do sine x divided by x. Okay, zoom out. Sorry, zoom in. If I trace, notice there's a hole there, right? See that hole? Now, why is that happening? If you think about it, sine x roughly equals x when x approaches 0. When x is super tiny, if you plug in 0.001, sine of 0.001 is pretty darn close to 0.001. So they're going to be very similar to each other, x and sine x, as x gets closer and closer to 0. That's why that's happening. Same thing with tangent. If I replace this with tan, I mean, the graph looks kind of funky, but same exact thing. Tangent x and x are pretty much the same thing when x gets super tiny. If you were to evaluate it at x like 0.01 or whatever, right? So that's why we have these statements here. Okay, we have those statements. Now, things that get a little bit interesting here. When these are the same, like 5x or 5x or 11x or 11x, it's still going to be 1. It's still going to be 1. And here's the reason why. Let theta equal 5x. So guess what? X equals theta over 5, right? So if I were to rewrite this limit, you have the limit. Now, if x is approaching theta over 5, I'm going to say, replace x with theta over 5, approaches 0, of sine theta over theta, right? So see what I just did? I replaced 5x with theta, right? So theta, or any alpha, beta, I don't care. And this x changes theta to 5. Well, if theta over 5 is approaching 0, what's theta approaching then? 0, of course. If theta over 5 is approaching 0, then the variable itself is approaching 0. And so we know this. So now what kicks into play? That kicks in, right? So we know that this is x, y, z, it's all arbitrary disorder, right? So I know that's going to be 1 anyway. So who cares if you put a variable in front, right? Here. As long as these are identical, this will always be null. So if I'm putting 0.001, that's 0.005. The sine of 0.05 is basically 0.05. That's what's happening. Now, but the second example is kind of funny. I'll tell you the quick and easy way, but I'm going to show you more formally why this works. The answer is just 9. Just 9. And there's actually a property that you can lean on that'll work all the time. When you have this, the answer is just k. Now, this is when the bottom is plain old x, but the top has a variable. So the limit is the variable itself. Why does that true? Why does that work? You good? No, it's not rhetorical. That's actually, I do want you to explain. Talk to us. Tell us. Well, kind of. Let's do the same formality we had last time, right? Let's do the same formality as last time. Let's say we have that, right? So you have the limit as theta over 9 approaches 0, which is basically 0. And you have sine of theta over theta over 9, right? So what happens now? It's basically the same thing as theta is approaching 0, right? But now it's going to be 9 times sine theta over theta, right? And what's
And now these are little problems. What's this one? And that, what's that? 9. There we go.
so that becomes 9 times 1, which is 9. That's the reason why. So if I do ask you to show it, I have to see that work. But ultimately, just so you know,
I'm probably not gonna ask that so much because we're gonna do lots of other limits and like some crazy ones. So this is something that kind of will be part of a bigger problem. But will be part of a bigger problem.
so you can just lean on that property. Here, what do you think we should do for B? What do you guys think?
Factor on the x on the top.
Yeah, or I could break up the fractions too. Actually, I'd do that. I'd break up the fractions. Okay. So it's 3 sine x over x. Plus 1, right? Would you guys agree? What was that, sorry? Yeah, or at this point, you just know it's going to be that. So I'm totally cool with that. You don't have to get too formal. I mean,
Yeah, it should be technically right. Lowest x plus 0, 3 sine x plus lowest x plus 0, 1. Yeah, it should, but
it's okay. At this point, I think you guys know what's going on. 3 plus 1 is 4. Because trust me, we're going to be doing more intense stuff later on. So, okay. How about this? Why don't you guys try C and D? See how it goes. All 3 is a screen. And then we'll move on to example 3 after that.
What's really
C and D. Seen a Lion King?
Yes.
Good.
Oh, wait, I'm so smart, it's just 30. Yeah. No, I can explain, This is right. No, it's
2, dude.
No, it is 2. It is 2. I got it.
Wow.
This,
Is this what?
you know, sine 6x over x. This is a k.
Yeah,
So this is like.
yeah. What
So,
do you think?
what did I say? Yeah, so I was like, oh, it's just that, but that's not how you do it. Wow. Yeah, no, that's not.
Here we go, guys.
These are both excellent test problems. These two. So you can get a little trade with fractions. Fractions are a good deal. I trust you guys to find it. But yeah, there's a reason why some people like you do like non-AP calculus, or they do calculus much later on, and they're kind of passed along, never really mastered fractions. Yeah, they're gonna have a hard time with stuff. Because you gotta learn how to decompose the ones. Notice I factor up the x, go to the party of the product. And like goes over here, right? 4% down as a product. 5x and x. And then you do separately. I got my answer, so.
We're okay at this? We're good? No questions? Okay, can I clear the screen? No? Yeah, okay. Oh, no, I feel still copying, sorry. Here, I'll just wait. All right, let's keep moving, guys. Example 3. It's the same thing. We're gonna do the conjugate. Is that right? Is that what I want to do? Hold on a sec. Give me 1 sec here. No, because it's gonna be a little funny because it's a 4th root.
Yeah.
Well, the pop is still gonna kill it.
Actually, I think we might still be okay. +1.
Yeah, if you do this.
Yeah, let's do this. Let's get started. Okay. I'm just a little hesitant here.
Don't make her think that they-
Think about her.
You have to be like, people a lot of that.
Okay. So if you do the 4th root times itself, it actually becomes a square root. Okay. You still have a problem, right? And why was that
X is a square root? How did that happen? Yeah, so it's the 4th root square, which is a square root.
So then you have to do it again. That's why I was a little hesitant here. What was that? Yeah, then you gotta do it again. And then we should be okay after that. It's okay. They'll cancel down below. Okay. And I don't want to cancel too much, so I just canceled the ones. I want to write one more time. I know it's kind of a pain. Keep writing it. Okay.
Like one to like the 1 billion. I just think so.
It's your one.
That should be You guys get 1/4?
Yeah.
Yep, there we go. Yep. Okay, I think we're all good there. Okay, let's keep moving, guys. We're doing great here. It might be a little too ambitious to get to page 4. You know what? Let's stop there for today. Let's stop there. I think it's a little too much. I could wrap this up on Monday, and we should be fine for doing more on. Oh, and I don't see you guys. All sophomores are gone, right? Except sophomore Wednesday, yeah. Yeah, I'm gonna have to push up the tests. Okay. Yes, I'll do self video.
Like, oh my God, I can't, like, I can't really do it.